your invitation here. So in this slide, I wanted to thank all of my collaborators in this work. Yeah. It's not working now. Okay. So, where are we applying the scattering calculations in particle physics? So, of course, the most important application is calculating the masses of low-lying hadrons. But besides that, there are a number of important applications. So, for example, the gamma to pi contribution to the G-2 also uses scattering approaches. And the nucleon neutrino scattering experiment at Dune, they also using scattering approaches in order to understand theoretically the result of the experiment. And also, if you wanted to study the nucleon structure and the excited states contributions there, the scattering is unavoidable. And our main goal, to completely understand the nucleon interactions and build the nuclear physics out of Lattice QCD at the end. So then let's just put on the map what I am going to present here about scattering. In low energy scattering, very low energy scattering, you usually have some approximation to the potential to leading order, to next to leading order in perturbation theory. And this works somehow with low energy, as you can see from this picture. So you have the nuclear effective field theory, and you can calculate basically the scattering phase shift, and you have a good description using just the potential. However, at very high energy, where the hadrons are no longer the definite degrees of freedom, but also the quarks are there, you have to consider Parton distribution functions. And in my talk, I wanted to concentrate on the energy region between these two extremes. So so-called intermediate energy window, where the dominant hadrons, the low-lying hadrons and the low-lying resonances also contribute to the scattering. And in this case, non-perturbative methods are essential because perturbation theory doesn't work. Okay. So what we use is lattice quantum chromodynamics. We basically discretize the theory of quantum chromodynamics on a lattice. This will be a statistical mechanical system on a four-dimensional space-time lattice. And you can see here as an example. So it's statistically similar as the easy model, but it's much more complicated since it's four-dimensional, and the degrees of freedom are color and spin or vectors on each side, and SU3 links and SU3 matrices on each links. So it's much more complicated than the easy model, but the main structure, I mean, the building blocks are similar. So we also have a partition function through which we actually compute observables. The very important point is that all of our calculations are done in imaginary time. So in the four-dimensional lattice, the fourth direction is not really the time, but it's corresponding to the temperature, and its infinite time extent will mean, in our case, that zero temperature. So we, I partially, I called this SQCD basically.
People don't know the determinant is H.
Yes. So sorry. I inevitably I understand this in the SQCD term, but that's very important because that makes the theory actually non-local. And so what we usually do is we have these 4 parameters in the theory. So the beta is the gauge coupling, the MUD, MS, and MC are the quark masses. And what we are doing is choosing 4 physical quantity to fix these parameters. And after this parameter fixing, all of our calculations will be actually predictions.
Can you please elaborate a little bit what you mentioned about
the time? The real, I mean, if you write out the path integral formulation of quantum chromodynamics, that will be sum over all configurations e to the is. And what we are doing now is to rotate to imaginary time in order to have exponential damping in the space of the parameters. So in order to be able to compute these integrals. And basically this means that we basically just change we just transform t to minus it, and yes, so in this sense, if you write it as a transfer matrix formulation, it will be e to the minus h over t. So like if you wrote the Boltzmann factor, and yeah. Yeah.
In the simplest answer, we do have a 4-dimensional lattice. 3 are spatial directions and 1 is time direction. So that's interpretation. Don't confuse people with temperature. Okay, so we do the main message that we do 0 temperature metric setting. 0 temperature.
Yeah.
We have a lattice in 3 dimensions and time at 0 time, I think.
Yeah.
I think you have to spend a lot of time.
Yeah. Okay.
Sorry.
No problem. Thank you very much. Then let's continue what we are computing exactly on the lattice. So we are computing correlation functions, which is basically 2-point functions. Like here, where we have an excitation creation operator at time 0 and an annihilation operator at time t, and we are contracting all the possible combinations between these two. So in this case, for the nucleon contains 3 quarks in both sides. So you have to contract these 3 quarks in all possible ways, and this is the nucleon 2-point function, for example. And how this is related to the mass or energy that we wanted to take. So just if you write this. If you insert here a sum over the eigenstates of the Hamiltonian n, you will get this sum, which contains actually the quantities that we are interested in, so the energies. but of course, the exponential functions are not, and so they are not form an orthogonal function series. So in order to determine this En, it's a quite complicated task. However, if we are just interested in the first En, so the mass of the particle, that can be reasonably well accomplished. So this is what we are trying to do. So we are basically interested in asymptotic states and only the first few. For the first energy level, which should be which corresponds to the mass of the particle in question. And of course, if we put the particle inside the box, then we have some finite volume dependence that we have to care about, due to the fact that if your box is periodic, then the propagation from this mirror charges to the final point gives also contribution. These are suppressed by e to the minus energy times L. However, they could be sizable if your box is small enough. So, but you really have to take, if you want to compute a physical quantity, is this tree limit in this order, basically. So you have to take the thermodynamic limit, L goes to infinity, in order to remove this exponential dependence. You have to take the continuum limit, and you have to be at the physical point, at physical quark masses. Okay. However, most of these particles listed here are not stable particles, so they are not eigenstates of the Hamiltonian. They decay further, and therefore we basically cannot determine their masses so easily as done for the stable particles. So they are they show actually resonant behavior. And here is the point where the resonances come in. And yeah, if you just look in a textbook about resonances, you will find out that how you the way you calculate the properties of the resonance is basically you have an approximation to the potential, and from the potential you compute the so-called scattering amplitude. And if the scattering amplitude have post-negative energies, negative real energies, then the potential has some bound states. And if the potential has a branch scattered positive energies, this will be the scattering state. And in the case of pole below the positive real axis, this this will be the resonance. And also, if you study experimentally the resonances, so you compute cross sections, and you see a bump in the cross section as a function of the energy. So you basically study real-time processes with asymptotically separated states, but both of these ingredients are not available in our lattice calculation, because the states, the resonance decays via strong interaction in our case, and they are not asymptotic states. So we have to do something else than computing the potential or doing this scattering experiment on a computer. And yeah, there is also a no-go theorem about this. The direct determination of scattering quantities in a finite volume is impossible. So what can we use instead of this? We can use how the finite volume influences the two-hadron interacting spectrum. It turns out that due to the finite volume, there will be an interaction between the particles, and the energy levels will shift. And this shift will be dependent on the volume, actually, and the volume dependence of this shift will give us information about the resonance. And yeah, this will be the main topic of my talk today. How we are doing this precisely? So we turn the finite volume to an advantage rather than a disadvantage, and we use this kind of Luescher formula, which relates the scattering amplitude. So a matrix in the scattering channels and partial waves to a geometric function f, which is known. And we basically solve this determinant equation. And here is a small example of what I mean. So these are actually from an old paper by a 5 to the 4 calculation where you can afford to calculate a number of different volumes. So here you calculated the two-particle spectrum for several volumes, and in each volume, for each energy level, you can calculate this phase shift quantity, which is plotted in the bottom. And if you know this phase shift as a function of the center of mass energy, then you have information about the scattering amplitude. And this is what makes us happy about studying resonances. So basically, from the two-particle spectrum, you can calculate the phase shift, and from the phase shift, you can get information how this function, this scattering amplitude will look like. And yeah, of course, these are an idealistic case because it simulated several volumes, and several volumes is very expensive, 4-dimensional QCD. And also there is, if you go to the physical point, this threshold, which about which this relation is correct, is very low actually. So what we are doing, instead of computing different volumes, we probe this relation for different momentum, and we try to calculate energy levels, as many energy levels as possible using the different momenta. And so this is basically one of our earlier results about pi scattering. But here we relatively have a high precision on the spectrum and a very nice description of the resonance. But so in my case, now I will talk about baryon resonances, which are difficult because the signal to noise ratio for the nucleon is much worse than the pion. Okay, and another challenge which I am talking about, that this formula is working only below the two-particle or in this case, in the pion case, the three-particle threshold. However, we can actually check using experimental data, so-called inelasticity, to check whether the scattering will be inelastic also behind the threshold which we are interested in. And here I show that the threshold at the physical point is somewhere in 1.2 GeV. However, the scattering is elastic up to good precision, up to 1.4 GeV. So we can use computed energy levels in this kind of Luescher procedure up to this point on. Okay, then this is basically our workflow. So our calculation actually takes, so first we compute diagrams, which basically means we're doing inversions of the Dirac matrix and weak contractions. And then we produce we produce correlation matrices from the diagrams. We project this correlation matrices to irreducible representations, and then we calculate the two-hadron spectrum. From the two-hadron spectrum, the phase shift, and from the phase shift, the parameter of the resonance. And here I basically just showed this diagram in order to illustrate the cost of each part of the calculation. So this EM means the inversion. So as you can see here, they are dominating the calculation. And which is also expensive is the contraction, so-called reduction in this figure. Which is sizable. The recombination part is also quite expensive, but not that much. And the most cheap one is the post-production, of course. And for this kind of thing, we use supercomputers and codes that I will be talking about now, actually. So in our first case, we compute the diagrams between the two hadrons, basically Feynman diagrams. So in this figure, I illustrate how you can contract two pion nucleon pair at source to the sink. So basically, you have 4 different kind of topology. The simplest one is where the nucleon goes to the nucleon and the pion goes to the pion. So this is the simplest one. There is no interchanging between the two. But this is also quite complicated, since here you have to multiply 3 objects with this size. And this means that per lattice site, you have to follow this operation where the Latin indices are color indices and the Greek indices are the spinor indices. And this is very tedious, and you have to do this at every lattice site. But this is also suggesting that this is an ideal task for a GPU kernel. And what we are doing in the software package Plasma developed by us is to basically do this kind of multiplication at the lattice site by the GPU itself. So it's quite fast. And here I also wanted to mention that these numbers for the inversion should be much larger if we do not use the highly optimized inverter from QDAR. This is developed by an external collaboration by NVIDIA. Okay, so in the last slide I mentioned the simplest case of the pion diagrams. Now I wanted to tell you a bit more about how we handled the difficult case when there are basically 2 sums computed which are not independent. So we have to compute a sum at the nucleon and at the pion. And you can see this is the diagram we compute, and this 2 sum is actually connected through this propagator. And what we are doing is basically that the problematic is this green line, so which goes from sink to sink. Basically, this means that we have to go from every lattice site to every other lattice site. And to even store this information is impossible. And what we are doing is basically we estimate this stochastically. We're using a few random vectors, and on these random vectors we do the inversion, and we approximate the propagator using just the spectral decomposition. And basically in this way we cut these diagrams into 2 factors, and we calculate each factor separately, and then we combine these factors. So the advantage of this method is also that if you consider the different kind of diagrams mentioned here, they share several these kind of factors, and then you don't have to recompute them when you compute another diagram. And just here to mention how our code process works if we scale with the number of GPUs, it's basically very close to the ideal scaling. So the parallelization of the contractions work quite nicely. Also, the CUDA part, the inversion part works actually nice because they are anyway small numbers, even if the scaling is not so good. So the next step, if we calculated the correlation matrices for the I equal 3/2 isospin. This means that we basically have a 3/2 vector. We have a spinor indices alpha and the vector isospin indices. So which basically, if we are in the finite volume, these are no longer the correct indices for all Hamiltonian. So this is because in the finite volume, we don't have the full rotational symmetry of the continuum. So we have only this kind of symmetries that are showing here actually. So we consider these three kind of total momentum, and in each case I listed here or in this figure the possible transformation that leaves that is basically symmetry. Basically in the center of mass frame, we have the symmetry group instead of the continuum rotation group, the double cover of the octahedral group, and they have actually finite number of irreducible representations, as listed here. For example, in the center of mass frame, we have the HG, and we have G1, G2 in the first moving frame. And what is important is that, these errors actually are dominant. For example, the HG is dominant 3/2 contributions, but they also have contributions from the 5/2 isospin case. So we have to make this assumption at the end that this can be actually neglected. Okay, so how this projection actually works in practice? So we actually change degrees of freedom from the isospin and spin index to irreducible representation rho, and occurrence. Yeah.
You should explain to them the problem of working on a discrete lattice.
Yeah. Yeah. So basically,
you have symmetry, you have rotating symmetry. So quantities are well defined.
Yes. So
here the problem is to break this symmetry because taking a continuum space is discretized, right? So that's the big problem. You break rotational symmetry. You break restoration symmetry. And these symmetries affect what is conserved only.
Yeah, I ask you something
Yeah.
more basic.
Yes.
Why do we need and circular. Okay, so Ferenc just because as also Dina said,
Yeah.
I'm not expert at all. So just very simple thing. Why do we need to use this lattice presentation of space? Typically, in n-body problem, what we are doing is we are discretizing time, of course, then you have the domain, and then you have something that is moving within the domain. Do you need this discretization in space that breaks the symmetries in a very nice explain?
Yes. So we basically have a finite lattice space in the space by construction. So we have so if you consider all lattices. Yeah.
Okay, quantum have infinite degrees of freedom. So if you write an equation, if you write the Lagrange or the equation of the theory, right? Write it on paper. It's not like classical physics. This is not where we go because there are infinities. In quantum physics, the vacuum is not a vacuum. It has particles and come over from the vacuum. There are infinite particles. So there are infinities. So before you calculate anything, you have to define what you mean by infinity. This is called regularization. You regularize it. One way to regularize it is to discretize it. Because then, if you think what is the number of momentums around, it's not infinity anymore. It's too high over the lattice space. Okay? So this is, you can think about this as going from infinite degrees of freedom to finite degrees of freedom. So you regularize it. This is what this discretization does. Among other things, yes, I know this is very
Yeah. Totally agree. Yeah.
This is the only way we know how to define the theory in a non-protective way. It doesn't matter what that means, but there is no other way to define QCD. We have to discretize it.
So, in order to start, let's say, solving the problem, you need to do this kind of discretization.
Yeah.
Because also the classical level will be infinite, again, potential states. Right? So, you have an ensemble, let's say, another states are infinite. But
They
you
don't
don't.
cut.
No, you don't count. You just follow the system and the system is a coding. You try to calculate this integral to converge.
Yeah.
Of course, I mean, you consider a finite number of particles, but the potential number of states is infinite.
Yeah.
You live with that. You just try to
The number of states, here is the same. The number of states is infinite. You don't exclude that. But in order to define the theory, because you not define that, it's not like classical. You still have the infinite states in your spectrum. This is not the issue.
So you cannot start.
You cannot even start doing anything before you recognize it.
Yes.
Okay, because quantum theory have infinities. Okay, so you have a vacuum in classical physics, the vacuum is a zero. In quantum physics, this is not a zero. Exactly. So this is why we are forced to do this thing. And this creates its own complications now that Ferenc is trying to explain. Okay, exactly.
Yes,
That's
exactly.
why what you learn in physics, you know, for example, that your momentum is conserved, or these are no longer values. And now this complicates a lot the analysis. And this is what you have to do now in analysis.
It would be interesting to see at some point this, but why do you need this?
So we basically, so to say, we change from the continuum spin and isospin degrees of freedom to the finite volume irreducible representation, row occurrences, and the combination of momenta degrees of freedom. And this is basically means that in terms of group theory, if we have the 12 by 12 group element that characterize the symmetry, this means basically that we block diagonalize it and obtain these irreducible representations. And yeah, here the picture is shown for the single data case, but in general, if we do the same procedure, for example, for the pion nucleon 2 hadron states, then we will have a matrix in terms of these variables, which is 8 by 8 for the G value, irreducible representations, and so on. So this can be a really a huge matrix. So, for example, the 30 by 30 matrix, this should be understood as per time slice. So we have such a large matrix per time slice, and this is what we have to deal with in order to compute the energy levels that we are looking for, that we can use in the Luescher analysis. And yeah, so this is the C matrices that I was talking about, the dimensions. And in order to get the ground state from this kind of correlation matrices, the usual way is to follow the so-called generalized eigenvalue problem, where you have so-called principal correlator times an eigenvector times the correlation matrix itself. And at the end, to obtain the energy level, you can fit the principal correlator with a simple exponential. And of course, the key point is to somehow construct this matrix from these large dimensions that I'm showing here, in order to have actually a good signal quality, kind of robustness. So if you include 1 or 2 additional directions in this matrix, the whole spectrum of the operator it's not good that if it changes. And also, I mean, each of the operators that you include in the matrix should have some non-zero projector to some eigenvector, and this is what I'm trying to show here. That so here consider just the 5 by 5 matrix out of this 9 by 9. And basically show that the first 2 operator actually dominates the first level that I got from the GVP, and also the second level is dominated by these first 2, and the others, the third up to the 5th interpolating operators are dominating the remaining levels. And yeah, if I change these operators a bit, then it's also robust. So this kind of good features I have for this HG listed here. Okay, but in order to be exactly sure to estimate the uncertainties here correctly, because this is the part that is really interesting to us, to calculate the 2 hadron spectrum, because that's what we use in the Luescher analysis as basically as a black box. This have to be estimated really correctly, and taking into account errors from fit ranges, from operator basis, as precisely as possible. In this reason, we use actually 3 methods to extract energy levels. The first is the usual GVP that I was talking about. The second is the so-called Hankel method, and the third is the analyis, which is basically just statistically sampling fit parameters according to the chi-square value of the fit function. And here I compare the three methods with each other. And you can see that there is a nice agreement between these three methods. This is for a particular irreducible representation for the first four level from that representation. And you can see that these lines here are the non-interacting levels, and they are separating, they are not overlapping with the actual levels that I'm computing, and this is important because this is what we want, that we have some shift from the non-interacting level according to the interaction, and this interaction that we want to study actually. Okay, so this is basically a summary plot of all spectrum determination, including all the ERAPs and all the methods. And you can see that we have many different, from many different levels, successfully computed so-called phase shift where the non-interacting level is actually well separated between the energy levels we compute. And yeah, from now on, I will use this data in order to obtain the parameters of the resonance. Okay, so yeah, I have to be a bit faster. So the two particle and so what we now have done is, of course, what is written here. So the two particular energy levels in a finite box size L, this we have, and what we have to solve now is the kind of disaggregation that I mentioned already and showed examples already. So these matrices are taken in the angular momentum space, and for example, for the L equal 1, we have a one-to-one correspondence between the phase shift and the energy levels, and this will be the easiest case. So here on the right-hand side, I just show two plots what we are doing, but explains actually what we are doing. So we are computing these blue curves, which is the Luescher finite volume function, and the red curve, which is just the parametrization of the scattering amplitude, assuming a resonance. And what we are interested in is the crossing point of these curves. So those will be the prediction of the finite volume energy levels.
Ferenc, we are really running out of time.
Yeah.
I don't know if you want to wrap up.
Yeah.
Finish your talk.
Yeah. So here I just show that basically how we use for which parameterization we choose for the resonance. So for the L equal 1 case, we choose the Breit-Wigner parameterization for the phase shift. The L equal 0 case, just the scattering length. And yeah, these are basically not so important. And this is the kind of important thing. So what we compute, what our task is that given resonance mass, resonance width, and the scattering length, we have to compute finite volume energy levels via this Luescher transformation, and compare this to the energy levels that we computed on the lattice. So we can set up a chi-square minimalization in order to fit these three parameters. And this is a technical issue that computing this kind of predicted energy levels is quite expensive. Therefore, we can use a multi-dimensional spline approximation to it. And yeah, this is the final figure that I wanted to show you. Basically, this shows the final value of the fit parameter that I obtained for the resonance using the above mentioned procedure. so 1,260 MeV for the resonance mass, and a very large, quite good value for the resonance width, but with a very large error, and the fit actually works quite well. Yeah, so these are not so important. That what I wanted to mention lastly, that why I got quite a large error on the width. And here I just wanted to show you a presentation, a simulation, basically a GIF, in order to illustrate that if I change the width, then how the predicted energy levels changes. So as you can see here, I changed the width basically 3 orders of magnitude, and the energy level, the predicted energy level, basically doesn't change. So and this is the reason why I have this kind of very large error on the width here, because itself the quantization condition does not does not restrict the value of the width correctly. So, but why is that? Okay, the first thing is that so here we are competing. Here we are two competing effects. So the first is the exponential finite L dependence that I mentioned in the beginning of the talk, that we want to get rid of, and the second is the power law finite L dependence that we obtain the sinai. And in order to be large, the second, and small the first, that is a non-trivial issue. And here on the plot, I show you that for ns equal 48, this is the second effect, this power law L dependence is quite large. However, in our case, the 64 is really reasonably smaller. And even if, I mean, doing the 96, it's even much smaller. So just to conclude, there is a lot of effort going on in order to calculate the properties of the delta resonance mentioned here in this table. And in our case, we are basically the first to calculate it on at the physical point exactly. And yeah, this is the result which I showed you. And yeah, just an outlook. So we are now using ensemble causal lattice spacing and smaller volume basically to basically get some confidence on the width as well. And we use also other kind of discretizations. What we are trying to do now is also doing the other isospin channel, the I equal 1/2 case. And thank you very much for your attention. Just I wanted to thank you also the supercomputers centers that gave us allocations to compute this project. Thank you very much. Yeah. Thank you very much.
Any questions or comments?
So Ferenc, just generalizing for the last
yes. Yes. So this is mainly related to this kind of small animation that I showed you. So here, basically started from 51 MeV the width, and changed these two lines, which is the prediction of the Luescher quantization condition, to these two lattice levels that I include as a horizontal bars. And yeah, they are basically compatible with the lattice levels in all of this range. And this is what we are but actually this kind of finite dependence is very small in our case. I mean, in terms of the width. So for the resonance mass, basically the location of the inflection point in this curve that can be reasonably well determined. But the derivative at the at the inflection point, that yeah.
So you can decrease a lot of lattice size.
Yes, yes. So what we are trying to do now is to compute the same kind of thing on a smaller lattice, of course, larger lattice spacing. But yeah. So this is a kind of difficulty in this kind of calculations, but we are seeing now because no one has calculated before at the physical point, and I mean, if you see this kind of plot that I was mentioning for the pi case, so here we have a very good control over the width and over the resonance mass as well. Of course, this is pi scattering and that larger than physical pion mass. Mm-hmm.
Slides, if you show the correlation function. How long does it take to compute?
What we are compute is basically this kind of 2-point functions where we so in terms of the nucleon here as an example. Sorry. As an example, so we are computing the propagation that one quark from here to here, the other quark also, and the third quark as well. We therefore just multiply these propagators together, and doing basically a Fourier transform in order to get on that. Yeah, basically, so the decay. I mean basically the decay will be what we are interested in. So how this correlation decays depends on the mass, and that's what we are after. And basically that's what we are determining. So yeah, so
question from Panayota. You want to try to answer a question?
Hello, can you hear me?
Yes. Go ahead.
Thank you, Ferenc, for a lovely talk. A question coming from not an expert from a different field. I was wondering, what are the next advances in your field, and what would be your future work? Be interesting to know.
Yeah. So what are we after is that. Basically, I said that this kind of Luescher formula that we are now analyzing is valid up to the pion threshold, where really, I mean, 3 particles interact, and what the field are working on actually is to extend this two-particle quantization condition in order to include also the third particle and basically extend this domain that when we can apply this kind of method to compute the resonances. So this is particularly interesting because we can have then included more energy levels further up in the spectrum and don't have to rely on such a small number of levels. But I basically, I have here relatively quite a lot of levels, but they are yes, some very close to the non-interacting one and with quite a large error bars. So we really gain a lot if we include more levels here in this field. And this will become available if we can extend the quantization condition in this direction.
Thanks a lot.
You're welcome. Yeah. So this this ensemble is the there was a technical slide. Here. The 2 + 1 + 1 0.28 physical point ensemble, so the 64 cubed ensemble, and what we are doing now is the NF equal to 0.09 Fermi lattice spacing ensemble, with 48 spatial sites. Yeah, this would become more interesting for me actually. Yeah. Maybe I hope that that this exponential finite volume effects will be still small. And, yeah. This will be interesting for us. Yeah. Thank you.
Okay, thank you, Ferenc, for this very interesting seminar. Thank you, everybody, for joining. So let's thank our speaker again.
Thank you.
And have a good day. Have a good afternoon.
Thank you.